Hey, how's it going? It's Mr. Farrell here. This is a physics help video on Newton's law of universal gravitation. So we started working on this, I think about a week ago, and we're just going to go over how to solve some problems working with this equation. The two types of problems we're going to solve are one, when you are working with the equation and trying to solve for the gravitational force. The other problem is when you are working through the problem and trying to solve for the distance apart that the objects are. All right, so give me 1 second and we'll get started. Awesome. So to start things off, let's just briefly go over Newton's universal gravitation equation. So F is the gravitational force, right? That is the force of gravity that the object feels, right? The larger that force is, the more gravity that object feels. So this is what we traditionally think of when we talk about the weight of an object. It is how much gravitational force are they feeling? That's what makes it feel heavy or light, okay? Over here, we see the gravitational constant. So this is a uppercase G. All right, the gravitational constant has a very specific number. It's not something that you would calculate in a problem. You're not gonna be asked to solve for the gravitational constant. The gravitational constant is always given to you. And if it's not stated in the problem, you always know what it is. It is 6.673 times 10 to the negative 11th power, and the units are newtons times meters squared divided by kilograms squared. So it's always going to be the same thing, whether it's mentioned in the problem or not. This is what it's going to be, and you're always going to have to use it in the problem, okay? Moving over, we have the mass of object 1. We label that with an M subscript 1. Now notice that we put the 1 at the bottom. That's called a subscript. That means that there are more than one mass in the problem, and we're just trying to tell you which one is the mass of object 1, which one is the mass of object 2. Some students have asked me before, why don't we mark that at the top of the symbol, the top of the variable? And that's because when we write superscripts, or when we write numbers above letters, then that's telling you that is an exponent. So we don't want these to be confused for exponents, so we're going to write them at the bottom of the variable, the bottom of the letter. So this is the mass of object 1, this is the mass of object 2, and this is R, which is the distance apart that the objects are. And R is going to be squared. As you notice, we don't put it at the bottom of the R. We put it at the top because we're trying to say this distance is being squared. Now, some people have asked me before, why don't we use D for distance instead of R, or we've used delta X for distance or displacement before. Why don't we use displacement and, this delta X instead of using R? And the reason is when we talk about gravity, right? Let's think about the shape of the Earth. Let me go ahead and erase all this. Let's think about the shape of the Earth. It's a big circle, right? So if we have an object or a person that's on the surface of the Earth, and we're trying to figure out the gravitational force on that person, the distance from the center of the Earth, the center of gravity of the Earth, to the person is going to be the radius of the circle. So it makes sense to talk about gravity in terms of R, a radius, because that's how far away something on the surface of that planet or that object would be, okay? So that's why we use R instead of D or delta X for displacement when it comes to this equation, all right? So we're going to be doing two different problems like I mentioned before. First, we're calculating the gravitational force. Then we're going to calculate the distance, that R distance for the equation. So I'm going to go ahead and read two problems. These are both from homework set 7. All right, the homework set if you're just watching this video for help, don't worry about the homework set situation. But I'm gonna go ahead and read the problem. So if you need to kind of slow things down, feel free to pause the video on the problem so you can write it down. I'm gonna show you real quick in the camera. So we're doing problem 1 right now. So again, feel free to pause the video so you can write down problem 1, okay? But I'm gonna go ahead and read it out. It says, the mass of object 1 is 3.4 times 10 to the 22nd power kilograms. The mass of object 2 is 5,028 kilograms. Both objects are 3,384,010 meters apart. What is the gravitational force between both objects? Okay, so what we're gonna do first is set up our ICE method, right? ICE stands for identify, categorize, equate, and evaluate. It's the process we use to go through our problems. So I'm gonna write that down, I, C, E, and E, okay? Some people call it the IC method. That works, either one works just fine, okay? So, again, you'll look at the problem as you wrote it down. I'll be reading through it. So the first step is to identify any measurement in the problem. So that is any number and its units, okay? So the measurements we come across in this problem are 3.4 times 10 to the 22nd kilograms. We also see 5,028 kilograms, and we see 3,384,010 meters, okay? Those are the only measurements, the only numbers with units that we see in this problem, okay? So the last thing we want to make sure to do in the identify step is we want to write a question mark, because we know we're looking for something. Even if we don't know what that thing is yet, we know we're going to be looking for something. So we need to remind ourselves about that. So we've got 3 different measurements here in our question mark. Now we're ready to move on to the categorize step. So after you've written down every measurement from the problem and your question mark, you're going to categorize everything up here as a variable, okay? So when we do that, it's important to read the problem, because the problem oftentimes tells you exactly what that measurement is. For example, the problem says the mass of object 1 is 3.4 times 10 to the 22nd power kilograms. Oftentimes students will see the units and not know what category it falls into. That is something you should practice to be able to identify a variable based on its units, right? Anytime we see kilograms, we know that's going to be mass. But even if you aren't really good at that right now, just make sure you read the problem. So the problem told us this was the mass of object 1. So we're going to label it M for mass and put a little 1 down there because that's mass 1. The problem tells us 5,000 kilograms is the mass of object 2. And it tells us that this 3 million meters is the distance apart. Now remember, we're using R for distance, so we're going to label that R. And the question asks us, what is the gravitational force between both objects? So let's go ahead, and we know we are looking for, our question is the force, the gravitational force. So now that we have all of this labeled, okay, we can go ahead and move on to our equate step. So we need to choose an equation that we're going to use to solve this problem. Now, obviously, we're working with Newton's law of gravity, so we know what equation we're going to be using. But if you didn't know, in order to figure out which equation you're going to use, you need to look at the variables that you have written in the categorize step and choose the equation that includes all those variables. That oftentimes is the one equation that you need to solve the problem. So for us, that's going to be force equals Newton's gravitational constant times m1 times m2 divided by r squared. Okay? So that's the equation we're going to use. Sometimes you might need to use two equations to solve a problem, but so far here we're only dealing with single equation problems, okay? So we have our equation selected. We know what each variable in the equation is going to be. Now we're just going to plug in our numbers and solve. Now, because f is our question mark, we're just going to leave it as f. We don't plug anything in for that. Now, g, remember, g is not written up here. G was not mentioned in our problem at all. However, we know what g is. G is the gravitational constant. It is always going to be the same number. We do not need to find g in our problem. We know what it is. It is 6.673 times 10 to the negative 11 newtons times meters squared over kilograms squared. Okay, so we know g, all right? Now we look at our equation to figure what we write next. Our equation says write m1. So the mass of object 1 is up here. That is 3.4 times 10 to the 22nd kilograms, all right? So we have G written, M1 written, now M2. M2 is 5,028 kilograms. All right? So we have every measurement written that corresponds to the variables in this numerator. Now we're going to write the denominator. All right? So that's our division line. And the denominator is r squared. So r is 3,384,010 meters. And now don't forget, r is squared. So we write this down for r, and then we go ahead and put our 2 up top to square it. So again, just to recap, where did all these numbers come from? Every number came from this equation. We know what g is. M1, we labeled it already. M2, we labeled it already. Write those down. Now r is up here, and we have to do r squared, so we just put our little 2 up top to square. Now let's go ahead and start getting into the problem solving, okay? So when we look at the numerator, we've got a couple different numbers written in exponential notation. So exponential notation is when you write a number and then multiply it by 10 to some exponent, okay? When we see numbers written in exponential notation, it's oftentimes because they're really large numbers and we're trying to simplify them or make them a little easier to see and deal with instead of writing out all the numbers, okay? So here we've got a really small number because it's 10 to the negative 11. And then over here we got a really big number, 10 to the 22nd power. So when we deal with exponential notation, we've got to handle it a little differently than we would standard multiplication. So the way we do that is we multiply every number that we see, and we're going to add our exponents together. So let me show you what I mean. Right here, this is 6.673, all right? So I'm going to underline that because that's just a plain number. There is no exponent there. Over here I see 3.4, that's a plain number. And over here I see 5,028. So all of these are plain numbers, all right? And we are going to use these plain numbers and multiply them together, okay? So let me go ahead and grab a calculator. All right, 6.673 times 3.4 times 5,028. All right, so when I add up all my numbers, and let me go ahead and write the division line again so I know my numerator and denominator. So I multiply all my numbers together, I get 114,076.2, and I'm going to round the 6 up to a 7, okay? So we've got our number, all right? Now we still have exponents that we have to deal with. Okay, we've got 10 to the negative 11, and we've got 10 to the 22nd. Now there's no exponent over here, that's fine. But if there was, then we would need to take that into account. All right, so what we're going to do here is we are going to add the exponents. So I know I'm still going to have times 10, but I don't know what power to put the 10 to. So negative 11 plus 22, because again, we're multiplying these numbers, so we're going to add the exponents. Whenever you multiply, you add exponents. So 10 to the negative 11 plus 10 to the 22nd is, or negative 11 plus 22, right? Adding those exponents equals 11, all right? So we write that down here. And now we're almost done. We just need to figure out our units for the numerator. All right? So when I look at my numerator and try to figure out the units, I need to see if anything cancels out. So I've got newtons times meters squared over kilograms squared, and then I've got kilograms times kilograms over here. Now because I've got kilograms squared in this denominator, I've got 2 of those kilograms being multiplied. I also have 2 kilograms being multiplied in the numerator. I can cancel those out. So that's 1, 2 kilograms. So I get to cancel out the kilograms to the second power. So that means my new unit for the numerator is going to be newtons times meters squared. Okay, it's my new unit for the numerator. All right, now let's go ahead and do this denominator. Now we have a big number here, 3,384,010 meters. That has to get squared. So let me go ahead and square that in my calculator. All right, so 3,384,010 squared. All right. So in my calculator, it says 1.145, it has a couple other numbers, and then it says E13, if you can see that, okay? Whenever your calculator says any number, E13, E14, E9, that means the exponent on the 10 is gonna be that number. So E13 means I'm gonna have 10 to the 13th power. Added to this, or not added to this number, but my 10 is going to be to the 13th power. Okay, so let me go ahead and write my answer. I got, again, 1.145, okay, and E13, so times 10 to the 13th power. Okay, that's what E13 means. So now I have my number, but I still need my units, okay? So over here, I've got meters squared, okay, because I squared my whole number. Now I also have to square my units. So the M is going to get squared as well, okay? So now we're almost there. All right, let me tilt this camera down a little bit just so we can see that more clearly. All right, so we're almost at our solution for the force. We just have a couple more things to do. So we've got a number in our numerator, a number in our denominator, an exponent in our numerator, exponent in our denominator. So these measurements are still written in exponential notation. So we're going to handle it just like we handled our numerator. We're going to deal with the numbers first, and then we're going to deal with our exponents separately. So let's go ahead and divide our numbers, right? So that's going to be this number here divided by the 1.145. So I'll throw that in the calculator. 114,076.27 divided by 1.145. All right. So for my answer, it gives me 99629.93. Okay, so that is the number that I get. But remember, I still need my exponents, okay? So in order to do that, let me go ahead and figure out what exponents I have. So I've got 10 to the 11th, and 10 to the 13th. Okay? So when we multiply, we're going to add our exponents. Since we are dividing here, we're going to subtract our exponents. So again, if you multiply, you add exponents. If you're dividing, you subtract exponents. So I'm going to do 11 minus 13. That's going to give me negative 2. So I'm going to multiply this number by 10 to the negative second power. All right, cool. And for my units, okay, I just need to see what cancels in my fraction. So I've got newtons times meters squared in the numerator and just meters squared in the denominator. So I'm going to cancel out the meters squared because they're the same in the numerator and denominator, and I'm left with newtons, which makes sense because newtons is the unit of force. All right, so the gravitational force that we get here is 996.29.93 times 10 to the negative second power. Now remember, when we're dealing with scientific notation, the answers can look a little different. For example, if you were to solve this out and take it out of exponential notation, I may have said scientific, when you take it out of exponential notation, you will notice that because this is 10 to the negative second power, your decimal place will move over 2. So this actual number, once we take it out of exponential notation, is just 996.2993, all right? But if it's an exponential notation, it can look like this, and that works as well, all right? So that's our first problem. We're gonna go over one more problem, and that is, for those of you all with homework set 7, we're gonna go over problem 4, okay? All right, so we're gonna write the ice method out again. All right, and so let me go ahead and write 4 up here because this is problem 4. Should have wrote that for problem 1. That's okay. So let me go ahead and take the homework set and bring it to the camera so those of you all watching can write down this problem if you don't have it. So again, you can pause the screen and write down the homework problem. We're going to be doing number 4. All right. Cool. So with that said, problem 4 says the mass of object 1 is 309,221 kilograms. The mass of object 2 is 1,236,144 kilograms. The gravitational force between both objects is 256 newtons. How far apart are the objects? Okay, so let me go ahead and write the measurements down. So object 1, I got 309,221 kilograms. For object 2, I have 1,236,144 kilograms. All right, the next number I see, next measurement is 256 newtons. Okay, and then that's all the measurements I have. So I make sure to add my question mark at the end because I know I'm looking for something, I just don't know what it is yet. So I'm gonna put my question mark down so I can make sure to figure out what I'm looking for. So that's the identify step. Now we're gonna do the categorize step. So again, you read the problem to figure out what each measurement is. So the problem tells us this number is the mass of object 1. This number is the mass of object 2. This number is the gravitational force between the objects, so that's F. And it asks us how far apart are the objects. That's going to be R. Okay? So I'm going to make a little bit of space right here. All right, need to move that E down a little bit because we're going to have to do a little bit of work. All right, so now we have all of these measurements labeled, okay, as variables. So now I go to the equate step. So again, we've been using the same equation. That equation has all these variables in it, and we're just talking about gravity, so we know it's going to be F equals gravitational constant times mass 1 times mass of object 2 divided by r squared. Okay? Now this is the equation we're going to use, but please notice that this equation is set up to solve for force. Now we already know the force, we need to find the distance apart. So that is r. Now r is currently in the denominator of this number. That is no good, or the denominator of this equation, that's no good to us. We need r to be in the numerator. So we need to move r out of the denominator into the numerator over here. So the way we do that is we multiply. Because if r is connected through division, then we're going to move it by doing multiplication. We need to disconnect it. So we're going to multiply by r squared on both sides so that we can disconnect this r. All right. So let me go ahead and cross out the r squared. All right. So now we are just left with r squared times F equals Newton's gravitational constant times m1 times m2. Okay? So this is a little bit better. We no longer have r squared in the denominator, so we're a step closer to being able to solve for r. Now we're not fully done yet, okay? And that's because F is now connected to r squared. We want r to be by itself, so we need to move F away from the r. We can't have F over here. So in order to do that, we need to do the opposite of the operation that's holding these two together. Currently they're being multiplied, so that means to separate them, we need to do division, okay? And we're not gonna divide by r because we wanna move the F away. So we wanna leave r there, we're just gonna divide by F. Okay, so we divide by. All right, so now we're gonna go ahead and plug in our measurements to solve for this problem. So we're just plugging it in exactly as it appears in the equation. So I'm gonna draw my square root symbol. Now remember, G is always the same. We didn't get that from the problem. It is just the gravitational constant. So we know the gravitational constant is always 6.673 times 10 to the negative 11 power. Newtons meters squared over kilograms squared. So those are the units. All right. Now we're going to multiply by mass 1, mass of object 1. Need to draw a longer sign. Mass of object 1 is 309,221 kilograms. All right. Now we do mass of object 2, which is 1,236,144 kilograms. Okay, all this stuff has been pre-labeled by us up here. We're just plugging it in to the spaces. Now we're going to do the division sign, and we're dividing by the force, which is 256 newtons. All right? So now we can go ahead and start solving this thing. So just like with any other exponential notation, we're going to multiply our numbers by each other, and we're going to add any exponents. Now we only have one exponent here, which is 10 to the negative 11, so we're just going to keep that and carry it down. So let me make another radical sign right here. All right, so again, 10 to the negative 11, we're just going to write that down here because we don't have any other exponents in the numerator. All right, so we're going to just bring that down. Now let's multiply those numbers. So we've got 6.673 times 309,221 times 1,236,144, and that equals 2.550, and we'll round that up to 0.7. And it says E12. So that means we're going to do 10 to the 12th power. That's our exponent, E12. All right. Now, here we find ourselves in an interesting situation where we now have another exponent to combine with this negative 11. And we use the same rules of combining exponents. When you are multiplying numbers, you add the exponent. So we've got 12 plus negative 11. And if you just throw that in your calculator, or just do the math, 12 plus negative 11 is going to be 1. So now our exponent is 10 to the first power. All right. Now, just like the last problem, we need to keep track of our units. So we've got kilograms squared, and that's in the denominator of this unit right here. But we've got 2 other kilograms up top. So those 2 kilograms cancel out with these 2 kilograms. So we're going to cross those out. And our unit for the numerator is newtons times meters squared. All right. So that's our numerator. Now our denominator, we don't have to do anything special to this. This is just the force. Unlike the last problem, it's not getting squared. It's just F. Okay. So we just go ahead and write that down here. Now we're going to go ahead and solve this problem, okay? We are going to keep our square root symbol because we're first going to go ahead and do the division inside the symbol. All right, so let me grab my calculator. I'm going to plug into the calculator 2.5507 times 10 raised to the first power. All right, I'm going to do that first, click equals, and now I'm going to divide by 256. So that gives me 0.0996, and I'm going to round it up to 4, okay? So that's what I have under the radical sign right now. Now to keep track of my units, I have newtons times meters squared, and I have newtons in the denominator. So my newtons cancel out, and I'm left with meters squared. All right, so I'm going to write meters squared over here for the units. So we're not done yet, right? Because we still have to take the square root of this to find our final answer. So let's go ahead and do that. Square root of 0.09964 equals 0.315, and we'll round that up to 7, okay? So that's our number, and our units are going to be the square root of meters squared, which is just meters. All right, so this is the answer for R. That's the distance apart that these objects are. Okay, so again, this is how you walk through these problems. It can be a lot of steps. You're working with some really big numbers, so make sure to keep track of your exponents properly. Make sure you're doing things one step at a time. And again, if you think you can do it in your head, just write it out on paper.